Hello everyone, welcome back to my channel. So I hope you are learning spectroscopic problem to solve the structure, and from my previous videos like 4 lecture on solder, IR, carbon NMR, proton NMR, and after that 3 episode. So now I'm going to discuss one more problem here, and this is a little bit tricky and a little bit difficult than the previous structures. So let's see the problem here. So you need to know the molecular formula. So here the molecular formula is given as C12H14O4. So remember one thing. First calculate the solder number. So solder is like there is no nitrogen or no halogen, so you can directly calculate as usual normal equation. So solder equation will be x plus 1 minus y over 2. So x is the carbon number and y is the hydrogen number. So x is here 12 plus 1 minus y, the hydrogen number, 14 over 2. So it will be like 13 minus 7. So the solder number will be 6. So according to our first technique, if you see the solder number 4 or more than 4, then you can think you might have the aromatic ring. So for the aromatic ring, there is a ring that for ring 1 and 3 double bond, 3 more. So total the solder number will be 4 for the aromatic ring. But you have the solder number 6. So still we have 2 more in our hand. Now look on the chemical formula. There are 4 oxygen. In my video, I told if you have 2 oxygen, then you can think either it has a carboxylic acid group or it has a ester group, COOR. Okay, so here you have the 4 oxygen. So in that case, it is a kind of tricky, but you can take that way. So you might have 2 of them in the structure, either the 2 carboxylic acid or 2 ester group. Anyone is possible. So first of all, let's see if you have the solder number more, like you have the benzene ring. It can be also proved by carbon NMR and proton NMR. So proton NMR, you should have the signal at 6.5 to 8.5. Let's see in the proton NMR. So you have the chemical signal at 7.5 to 8.5 or like 8.6, something like this. So you have the peak here, so you must have the aromatic ring. So I will discuss about the substitution because it is expanded, so it has a triplet, doublet, and a singlet kind of things. So I will go a little bit deep in this explanation, but first confirm that you have a benzene ring. So you have a benzene ring in this structure. Not only that, in your carbon NMR, as I mentioned before, you should have 110 to 160 signal peak. So that will also aromatic ring or the carbon-carbon double bond. So alkene carbon. So here before going to the alkene carbon, like we are not sure we have the alkene carbon or not, but since aromatic peak in the proton NMR showing like you have the aromatic ring, so definitely those peaks may be for the aromatic ring. So let's see the IR first before going to there. So IR will give you some more information. So as I mentioned, like you might have the carboxylic acid or the ester group, and maybe 2 of them because you have total 4 oxygen in your molecule. So for 2 oxygen for carboxylic acid or ester group, so 4 will be like double of those groups. So to be ester or the carboxylic acid, what should be in your IR? Definitely in your IR you should have a carbonyl peak. So we have a carbonyl peak here, so 1 carbonyl peak. So that is proving that you have a carbonyl group. And since I am suspecting it could be carboxylic acid or the ester, and in my previous video I said if you have the carbonyl group along with a peak around 3000 to 2500, like a ugliest broad band like this, so that could be like carboxylic acid peak. But here you are not seeing any ugly broad band from 2500 to 3000. in IR. So in your IR there is no carboxylic peak here. So in that case, you can think of like you don't have the carboxylic acid because the IR is not showing that peak, but definitely you have the carbonyl group and you have 4 oxygen, so you might have ester group. So in that case, let's see how we can determine that ester group. So you have the carbonyl group and definitely another oxygen should be ester group, OR, and it could be also proved by the proton NMR. Now go to the proton NMR. So what are the group you are getting from the proton NMR? So there is a triplet here at 1.5, around 1.5. So triplet means a carbon having 3 proton and where it is has a neighbor of another carbon have 2 proton. So that 2 proton is saying by, so if it is a B proton and A proton is like methyl proton, so A is saying that B proton, all of them, so that's why there are 2 neighbors. So 2 plus 1, that will be 3. 2 plus 1, 3, that means quartet. So you are seeing the quartet here, but definitely that B proton also will see A proton. So B proton has 3 neighbors, so 3 plus 1, that should be 3 plus 1 equal to 4, that then it will give you a quartet. So here at 4.5 is a quartet. So that quartet is at 4.5, that means definitely that carbon is next to oxygen, because you have the oxygen in your molecule, you don't have any nitrogen, you don't have any halogen, so definitely it could be only oxygen. So let's put that oxygen here. In that case, that oxygen will be with this carbon. So you have this group now. So we have this carbon, that group, and definitely since we are saying it is a ester, so you can now include that carbonyl group to make a ester group. So this part is showing in the aliphatic region, like you have the triplet and you have the quartet, and quartet is little downfield like around 4.5, and that's why it is next to the oxygen. So only the carbonyl group hand is open. Now in the aromatic region, we see that we have an aromatic ring, so aromatic ring should be connected with this carbon directly. Okay, so like here, so here. Now since we are saying we might have this group double of that, like 2 of that, so in our aromatic ring it should stay in the aromatic ring in such way, like so that the molecule is symmetric, and also you can get put those 2 group in this aromatic ring, so that you can get a triplet, doublet and singlet. And another thing here, if you see the expansion, you see the triplet, and that triplet also is split a little bit, not expanded quite good, but it is little bit splitted. And also this doublet is like also splitted another doublet. So this doublet, it looks like this, so that is called like doublet of doublet, and it is a triplet of doublet, and that is a small like triplet, small triplet. Okay, so why, how? So now there is no 2 doublets, so that's why this benzene ring is not 1,4 disubstituted. I'm saying again, it is not 1,4 disubstituted. So this benzene ring should be a little bit different position. So if you take this benzene ring here, and now to make a proton as a singlet, which is like a triplet actually, I will explain why it is triplet, but now assume that it is a singlet, it is a doublet and it is a triplet. Now for now just think that. So if you have a proton which has a 2 neighboring proton, like this proton, suppose this proton, and it has a 1 neighboring proton, it has another neighboring proton, so that A proton will be that triplet. So this is A and this is B, suppose. So B proton will see A only, so B will give you a doublet. So that is B. So you can take that signal is B. So it is a B. This signal is B, like, because B is saying doublet, and this B is also same. Okay, now you need to have a singlet. So if you put one group and one group here, so there will be another proton, it will be C, and that will be a C. So here in the proton NMR, you are now getting that position is open. So you can put a carbonyl group here, and then ester, and then CH2, then CH3, and same here. So you can put carbon here and oxygen and CH2 and then CH3. So here the same in both sides, and this molecule is symmetric. So here B proton is giving you the doublet because B is saying only A, and A is giving you a triplet because A is saying B, both B. And this molecule is kind of symmetric because of this ester group in both sides. So you can think how this is the symmetric molecule. So let's draw a line through the molecule. So this is a one half, like this is one half, one side one half, another side another half. So another important thing is benzene ring also can give you the meta coupling. Like if you have something group, like suppose here is one group and here is a one proton A and here is a one proton B, so that HA can see also the B, but since it is like a little bit far and also there is some group in the middle, that's why it will give you a W coupling or a small coupling, which is small splitting. So in our original structure here, the HC will see the B proton little bit, so it will see in both way, like B proton in both way. That's why AC will give you a very small triplet. That's why you are seeing the C group a small triplet. Same thing, the B proton will see HA as a single one proton, so it should give you a doublet. But B proton also can see little bit C proton, and that's why it is like B proton is giving you a doublet of doublet, like a small doublet. So this is like, this doublet is kind of like this. So this doublet and that another doublet. So this is doublet of doublet. Now for A proton, that A proton will see B proton and B proton, and also A proton is far away from the C proton. That's why it is not literally giving like good splitting. So you can take it as a triplet. So now from the carbon NMR also, if you see in the carbon NMR, if you look on the carbon NMR, so from this our projected structure, how many carbon or signal we should see in this NMR. So since it is a symmetric molecule, just assume one half of the structure. So here here you will see how many carbon, one carbon here, another carbon here, and another carbon here, and another carbon here, total 4 carbon, because other half also the same. So the HC carbon and HA carbon, they are two different carbon, and this ester group containing carbon and also the HB carbon, they are same, sorry, they are different. So if I put the number here, you can see that this is 1 and this is 2, this is another 2, and this is 3, and this is another 3, and last one is 4. So total 4 different carbon you will see in your structure. So here you will see the this part is expanded here, and you can see 1, 2, 3, 4. There are 4 carbon for the aromatic ring, and 1 carbon, that is like around 165. And as I mentioned in my previous videos, like 165 carbon is always for the ester. So not carboxylic acid. So that is another confirmation that you have the ester, not carboxylic acid. And in the DEPT NMR spectra, if you see here, the first peak in the carbon NMR, first peak is up. So normally for the DEPT, the up peak is either CH3 or CH. those are up. So you can see here the CH will show you up, CH3 show you up, and CH3 will be down, CH2. So here you can see one CH2 because one peak is down, and that is this peak, actually this peak. So that is the proof that this carbon is next to the oxygen. So that next to the oxygen is a CH2 peak, and this is around 50 to 60. So you have a CH2 peak, and all aromatic protons are up here. So you see like all aromatic carbons are up, and that should be 3 because 1 2 3. And another important thing in DEPT, the quaternary carbon, like which carbon doesn't have any hydrogen, those will not show up. So here you can see in the carbon NMR, we know like we have 4 carbon in the aromatic ring. So here the HC has a proton. In number 2 there is no proton, number 3 has a proton, and number 4 has a proton. So you'll see this number 1, number 3, and number 4 carbon in the DEPT. You will miss the number 2 because it doesn't have any hydrogen. So here you are seeing only 3 carbon in the carbon NMR. And definitely the ester group, that is also missing because that ester group also doesn't have any proton here. So that's why that carbon is not visible in the DEPT. So from this proton NMR and the carbon NMR and the IR, I hope you kind of get idea like how we are approaching for the structure. So DEPT also give you a little bit more important information, like how many CH2 peak you have and how many CH peak you have and how many peaks are missing, because in DEPT normally the carbon which doesn't have any proton, they will not show up. So like you will not see the ester carbon in the DEPT missing, and also in the 4 carbon of the real carbon NMR, but in the DEPT you will see 3 carbon because 1 carbon is quaternary carbon because that is attached with the ester group. So now finally I can show the structure. Let's draw again with a fresh way. So what we have from the carbon NMR and the proton NMR and the ester. So in the proton NMR, in the carbon NMR and the IR. So in the from the IR and the proton NMR, we got this, like we have a ester group like this, which has a CH2 next to the oxygen and CH3. Now we designed that our benzene ring should be a symmetric situation. So we have this carbon again and this CH2 next to it and also this CH3. And in the aromatic ring pattern signal, so you can get some idea if we put hydrogen here, HA, HB, and this is also the same and this is the same. So here the A will be a triplet and this is B, so B will be a doublet of doublet because B can see A, so it will give you a doublet. Also B can see that proton, like C proton, so that C proton also give you a little doublet. So that's why B is a doublet of doublet. A is like triplet, and C will see only B over the functional group, so that's why it will give you a triplet, a small triplet. So this is the structure like for this problem. And definitely if you, another thing I forgot to mention, so see the C proton is for one proton. So these integration value for 1 proton, and B proton also has 2 proton because you know that in both sides there are 2 protons. So this integration value is for 2 proton, and here the A proton also for that integration value for 1 proton. So you have total 4 proton in the aromatic ring. So with this level, so you can think like this is for 1 proton and this is for another proton. So this is for 2 proton, and similarly this is for 1 proton, 2 proton, and 3 proton. So total here you will see 3 proton. So from the molecule you can see that the first triplet is a 3 proton, then quartet, but it is around 4.5. That means that it is next to the oxygen, and it is for 2 proton. So you are seeing 2 proton, and in the aromatic ring you are seeing 4 proton for different proton for the 3 different signal, because 2 protons are same, b proton are same due to the molecular symmetry. So I hope you understand this, and if you have any question you can ask me and I can give you the answer for any certain specific question about this kind of NMR spectra and solving the structure. So I hope you enjoyed the video, and if you didn't um, subscribe my channel yet, just please subscribe my channel and watch my video and share my video to your friends and whoever interested to learn the NMR spectroscopy and IR spectroscopy to solve the structure. Thank you. Bye now.